All right, I'm back. We're on page 3 of Notes 29, Calc AB. So this is actually a post-AP exam topic for us. If you're in BC, it is very much a pre-AP exam topic, and you will need to know it. If you're in Calc 2, thanks for watching the video. All right, so we want to do the integral from 0 to infinity of x e to the negative x dx. So I can tell there's definitely a problem at infinity. So I'm going to start off by doing that. But also, I have a sense of where this is going because x e to the negative x definitely looks like an integration by parts situation. So let's start with the upper bound. So we'll use b goes to infinity, 0 to b, x e to the negative x dx. Okay, so what are we going to do? I'm going to do a little indefinite integral, I guess. Where would be a good lineup for it? I'm going to do it down here. I'm going to do a table method. So let's do, there's going to be a u, a v, and then the sign. So if you don't know how to do this, go watch those videos. So u is definitely going to be x, and in fact, it's going to go x, and then 1, and then 0. So you're not going to have to repeat this very many times or anything. So this column is always v, right? So from the integral, dv is e to the negative x. So v is negative e to the negative x. Then you keep integrating. So you'll get e to the negative x, and you would get negative e to the negative x again, but it's going to be times 0. For sine, it's actually just the sign that would go in front of the integral and integration by parts. So it would be first minus, and then it's plus because it's like a nested integral. You have minus, and then another integration by parts gives you another minus, so it's plus. Then on the next row, it would be the original minus, the minus from the second one, the minus from the third integration by parts, so minus overall, but that's going to zero out. So this will be, so we'll say equals the limit as b approaches infinity of, so it's negative, I'm going to write it as negative x over e to the x. It's negative x e to the negative x. But I'm going to write it as this because then when I fundamental theorem, it'll be a lot clearer what's going on. And then minus 1 over e to the negative x. That's a weird negative sign. Negative x. And we're going from 0 to b. Okay, so that'll be the limit as b approaches infinity of negative b over e to the b minus 1 over, oh wait, I'm sorry, I have an extra negative here. Get out of there. I had so much trouble even making that negative sign, then it turns out I didn't need it. So over e to the b. And I'm just going to say minus, when you plug in 0, you get 0 minus 1 over e to the 0 is 1, so minus 1. Now, the first part, it depends on how much work you want to do. I look at that and I say, by relative growth rates, b over e to the b is definitely going to be 0 because an exponential grows faster than a polynomial. And then 1 over e to the b is definitely 0. So this overall gives us 0 minus negative 1. So I think we get 1 overall as our final answer. So I think, well, first of all, I think we keep getting 1 as an answer, and that's a little suspicious. But I think that I would show exactly that amount of work. I mean, you can show a little more. You could do L'Hopital's. There's just like not enough room on the page, to be honest. So negative x goes from 0 to infinity. We get 1. Got it. All right. Let's take a look at this next problem, which I think is going to be the worst one that we do because there's two problems. You can't divide by 0, and 0 is in the interval. So we have, 0, and we're just going to go that way forever. 0 is a problem, though. So we're going to approach 0 from the right, and then we're going to infinity. So we're going to have to use a limit on that also. This is pretty crazy. So what do we do? You pick literally any number in between, I guess, 0 and infinity in this case. So I'm going to pick 1. And I will deal with this separately. I'm going to deal with first the part from 0 to 1. See if that converges. If that doesn't converge, I'm going to be done. So I'm hoping it doesn't. But it'll be the limit as its lower bound. So a approaches 0. Which way do you approach from? The right. That's an a. A to 1. of dx over root x, x plus 1. Luckily, I remember this antiderivative, or I can just like scroll back and find it. Plus, it'll be the upper bound that's the problem this time. So b approaches infinity from 1 to b of dx over root x, x plus 1. Okay, so if you recall, the antiderivative, which we did with u substitution on the previous page, was 2 tan inverse of root x. We're going to go from a to 1. Let's see what we get. So this will be the limit as a approaches 0 from the right, 2 tan inverse of root 1, which is just the tan inverse of 1, minus 2, so I should put this in parentheses, tan inverse of radical a. Okay, so this gives me, the inverse tangent of 1 is pi over 4. So this gives me pi over 2, well, 2 times pi over 4, so pi over 2. Inverse tangent of 0 is 0, so that part just gives me that. Let's now deal, so this will be equal to pi over 2 plus, let's do the second integral. The limit as b approaches infinity of, so same antiderivative, 2 tan inverse of root x, and we're going from 1 to b in this case, which will be the limit as b approaches infinity of 2 tan inverse of root b minus 2 tan inverse of 1. Trying to squeeze this in. All right, so what does arctan look like? Arctan looks like this, and it has horizontal asymptotes here and here. This is at negative pi over 2. This is at pi over 2. So if I go to infinity, I get pi over 2. 2 times pi over 2 is pi. The inverse tangent of 1 is pi over 4, so minus 2 times pi over 4, so minus pi over 2. So this part overall gives me pi over 2. So I think that overall, the final answer to this problem is pi over 2 plus pi over 2. It's just pi. So this one, let's check. So I'm getting pi as my answer to that. So here, integral of 1 over the square root, excuse me, of x plus 1, comma x. We're going from 0 to infinity. Pi, yes. It's very satisfying to get these right. I mean, there's like a lot that can go wrong along the way. Like I have a lot of experience with this, and I feel that way when I do these problems. Like so many potential pitfalls. You know, you could get an antiderivative wrong, which is probably the main way that you'll end up getting them wrong. You could get your notation wrong, just tons of things. All right, let's finish this last problem here, and then we'll say goodbye for the notes. So let's see, for what value of p does the integral converge? Okay, so the only problem is infinity, so we can deal with it as the limit as b approaches infinity of 1 to b. I'm going to write it as x to the negative p, and then dx. Okay, so that'll be the limit as b approaches infinity of, now when you integrate this, you're kind of tempted to write negative p plus 1, like plus 1 times the reciprocal. It's easier to write it as 1 minus p. So I'm going to say that this is 1 over 1 minus p times x to the 1 minus p. I just added 1, but I chose to rearrange how I wrote it. Instead of negative p plus 1, I wrote 1 minus p. I think it just makes it easier to like puzzle out what's going to happen here. And then we're going to go from 1 to b. So this is the limit as b approaches infinity of, so it's b to the 1 minus p over 1 minus p. And then minus, when we plug in 1, we just get 1 over 1 minus p. Okay, and we could put the parentheses all the way here. It doesn't really matter. One of the things that you notice immediately from this is that p cannot equal 1. So like right away you see p cannot be 1. Now let's think. If p can't be 1, there's like a lot of options here. P could be greater than 1, p can be less than 1, could P be negative? If P is negative, then we have a big problem, right? Because if P is negative, then 1 minus P, so if P is less than 0, then 1 minus P is greater than 0, and therefore B to the 1 minus P will go to infinity as B goes to infinity, so that diverges. Therefore, diverges. If P is between 0 and 1, what will happen? So if P is between 0 and 1, all right, so actually, honestly, so I said if P is less than 0, we had a problem. What if we just said if P is less than, I'm going to change this up and just, what if P is less than 1? If P is less than 1, we get a positive exponent. So I'm actually going to go through, I'm going to change this. I'm going to say if P is less than 1, and then this will change also. So if P is less than 1, then 1 minus P, so if P is less than 1, then 1 minus P is positive. So 1 minus P is greater than 0, which means that B stays in the numerator, right? It has a positive exponent. So the logic still holds true. So if P is less than 1, it diverges. If P is greater than 1, then 1 minus P is less than 0, which means that B goes in the denominator. So B to the 1 minus P will go to, well, it's not really, what do I want to say? This isn't going as well as I'd like it to, but it's okay. So B will go to B to the, what are we saying? B to the 1 minus P is in the denominator. And therefore, B to the 1 minus P over 1 minus P will go to 0, because that's all in the denominator, and B is going to infinity. So you're basically getting 1 over infinity at that point. We'll just talk our way through it. Getting 1 over infinity, which is definitely going to be 0. So we converge. Ooh, converge. Okay, so where could we write our final answer? I'm going to write it here because I have like this whole extra page that just like shows up when I get to the bottom of these notes. So I'm going to say, therefore, the integral from 1 to infinity of 1 over x to the p dx converges for p greater than 1 and diverges. Oh my God, what am I even writing? I was writing like diverges for p less than or equal to 1. So converges if p is equal to 1. Oh my God, converges if p is greater than 1. This is terrible. And diverges if p is less than or equal to 1. This is a big, big deal because later on you're going to see things called p-series, and the convergence or divergence of what's called a p-series is intimately related to this integral. And in fact, you already know what will make it converge. It's going to converge if p is greater than 1, diverge if p is less than or equal to 1. It's a big, big deal in Calc 2 when you're talking about infinite series, p-series, very famous. All right, so I'm going to call it a day on these notes. I don't think the discussion of this went perfectly, but I think you probably got the idea if you were following along with the words in addition to what I was writing. So here are your problems that you can screenshot. And let me scroll a little here, screenshot that, and then screenshot that. And then I don't know, this is the last Calc AB notes. Maybe I'll see you in another set of notes. Maybe I'll not see you again. Who knows? Hope this has been helpful, and take care. So see you later.